Welcome to today's deep dive. We'll be exploring the fascinating world of organic chemistry using Clayden's organic chemistry as our guide. I've always thought of it as, well, the chemistry of life, but I'm guessing it's more than that.
It is. You're right. It did start with that focus on living things. Then it sort of shifted to compounds found in coal. And now it really bridges both. It encompasses carbon compounds wherever they are.
So not just in us, but in the world around us too.
Exactly. Think about it. The vibrant dyes that color clothes and food, the epoxy resins that hold airplanes together, even the plastics we use every day. It's a field that touches nearly every part of our lives.
Oh, wow, yeah. Reading the text, I came across this food dye, fast green FCF. It's in so many things we eat. But I never thought about the chemistry behind it. It really brings home how organic chemistry shapes our choices, even down to the color of our food.
That's true. People see it as abstract subjects, but it's really intertwined with our daily lives.
Yeah.
While the applications are vast, at its core, it's about understanding the structure and behavior of these carbon compounds.
Right. And that brings us to the challenge of naming them. The textbook talks about systematic, IUPAC, and trivial names. It seems like chemists can't agree on just one system.
Well, think of it like having a formal name and a nickname. You use them in different contexts, right? It's the same with organic compounds. We might use the systematic name for clarity in scientific literature, but in the lab, we often stick to those familiar, trivial names.
So it's more about understanding the logic, not memorizing everything.
Exactly. The goal is to know what the name tells us about the structure, not getting bogged down in memorization.
Okay, that makes sense. But how do scientists even figure out the structure of these complex molecules in the first place? It's like solving a molecular jigsaw puzzle.
That's a great analogy. Just like any puzzle, you need the right tools. One powerful tool is X-ray crystallography. It allows scientists to create a 3D map of a molecule by analyzing how X-rays diffract off its electrons.
So it's like taking a molecular snapshot. But the text mentioned that this technique isn't perfect. It needs crystals and sometimes struggles to see lighter atoms like hydrogen.
Right. Imagine trying to photograph something moving really fast. It might come out blurry. Hydrogen atoms are so light, they're constantly vibrating, which makes them harder to pinpoint.
So how do scientists compensate for that? Do they just kind of infer where the hydrogens are based on the rest of the structure?
That's one approach. Luckily, we have other tools like mass spectrometry. This helps determine the molecule's weight and elemental composition. But what's really fascinating is that we can actually analyze the abundance of different isotopes within a molecule.
Isotopes, you mean like carbon-12 and carbon-13?
Exactly. By looking at the ratio of these isotopes, we get a more precise fingerprint of the molecule and confirm whether we're looking at the whole molecule or just a fragment.
It's like having multiple pieces of evidence to solve the molecular mystery.
Precisely. Each technique gives us a different piece of the puzzle, and by combining them, we can build a comprehensive picture of the molecule.
Okay, I'm starting to see how these techniques work together. Now, what about NMR? The textbook mentions it can even scan living human brains. That's incredible.
NMR, or nuclear magnetic resonance, is really versatile. Imagine a compass needle aligning itself with Earth's magnetic field. In NMR, we use a strong magnetic field to interact with the nuclei of atoms. Just like those tiny compass needles, the nuclei respond to this magnetic field, and by analyzing their signals, we can determine their arrangement within a molecule.
So it's like using the nuclei as tiny spies to map out the molecular landscape.
Exactly. And a key thing we look at is the chemical shift. It tells us about the electronic environment surrounding each atom. For example, an oxygen atom nearby can pull electrons away from a carbon atom, shifting its signal downfield.
It's like the oxygen is hogging the electron blanket.
Exactly. And those shifts give us crucial clues for solving the structure. Remember that unknown molecule with the formula C3H6O from the text?
Yes, I remember that.
Well, based on that formula alone, there are several possible structures. But by analyzing the chemical shifts of the carbon and hydrogen atoms in the NMR spectrum, we can narrow down the possibilities and eventually pinpoint the correct structure.
It's like having a molecular detective on the case. So NMR helps us understand not just what atoms are present, but also how they're connected and arranged in space.
You got it. It's a powerful tool for piecing together the molecular puzzle.
This is all so fascinating, but I'm also curious about another technique mentioned in the text. Infrared spectroscopy. How does that work?
Infrared IR spectroscopy focuses on the vibrations of bonds within a molecule. Think of it like each bond having its own unique dance move. Different types of bonds absorb specific frequencies of infrared light, and by analyzing which frequencies are absorbed, we can identify the types of bonds present.
So it's like each bond has its own signature rhythm that IR can detect. That's amazing. But can it tell us more than just what types of bonds are there?
Absolutely. Here's a fascinating detail. The strength of that absorption actually depends on the polarity of the bond. So a carbonyl group,
Yeah.
CO, has a strong absorption because it's very polar. But a CC double bond in a symmetrical molecule might have a weak or even absent absorption.
So IR can give us insights into both the presence and the nature of the bonds. That's incredible.
Exactly. Each spectroscopic technique provides a different layer of information, and by combining them, we get a richer understanding of the molecule.
Okay, I'm really starting to grasp the power of these tools. But what about the electrons themselves? How do scientists understand their behavior within a molecule?
That's where the concept of molecular orbitals comes in. Instead of electrons orbiting individual atoms like planets around the sun, we think of them as occupying molecular orbitals that spread over the entire molecule. These molecular orbitals are formed by combining atomic orbitals, much like combining Lego bricks to build a larger structure.
So it's like the electrons are sharing a molecular apartment complex instead of living in individual atomic houses. But how does this help us understand their behavior?
Well, let's take the simple example of a hydrogen molecule. When two hydrogen atoms come together, their one's atomic orbitals combine to form two new molecular orbitals. One is a bonding orbital, which is lower in energy and where the two electrons reside, holding the molecule together. The other is an antibonding orbital, which is higher in energy and usually empty.
So the electrons in the bonding orbital are the glue that holds the molecule together. It's literally the chemical bond.
Precisely. And by understanding the energies and shapes of these molecular orbitals, we can predict how molecules will react and form new bonds.
This is all so mind-blowing, but I'm still a bit fuzzy on hybridization. The textbook mentions something about reshaping orbitals. What's that all about?
Hybridization is a way of combining atomic orbitals to create new hybrid orbitals with different shapes and orientations, better suited for bonding. It's like interior decorating for atomic orbitals, optimizing the space for electron sharing.
Okay, I like that analogy, but can you give me a concrete example of how hybridization works?
Sure, take sp2 hybridization. Here, one sp orbital and two p orbitals on a carbon atom combine to form three equivalent sp2 hybrid orbitals. These hybrid orbitals explain the bonding in molecules like ethene, where the carbon atoms are double bonded.
So hybridization helps us understand the geometry and bonding patterns in molecules.
Exactly. It provides a framework for explaining why molecules have the shapes they do and how they interact with other molecules.
This is all incredibly fascinating. But the textbook kept mentioning the carbonyl group as being particularly important. Why is that?
The carbonyl group, with its carbon double bonded to an oxygen, is a real star in organic chemistry. Its reactivity comes from the difference in electronegativity between carbon and oxygen.
Electronegativity, that's how strongly an atom attracts electrons, right?
You got it. Oxygen is more electronegative than carbon, so it pulls electron density towards itself, creating a partial negative charge on the oxygen and a partial positive charge on the carbon.
So the carbon becomes a bit like a magnet for anything with extra electrons.
Exactly.
Ugh.
And that makes it susceptible to attack by nucleophiles,
Hmm.
species with electron pairs to donate. This polarization of the carbonyl group is the foundation for a wide range of reactions, making it incredibly versatile.
It sounds like the carbonyl group is the life of the organic chemistry party. But what are some examples of these nucleophiles that are drawn to it?
Well, one interesting example is the cyanide ion. Remember that reaction we talked about earlier where cyanide reacts with acetone to form an alcohol?
Right, that was fascinating.
That's a classic example of a nucleophile attacking a carbonyl group. The cyanide, with its lone pair of electrons, is attracted to the partially positive carbon in the carbonyl group and forms a new bond.
So it's like a molecular dance, with the cyanide drawn in by the allure of the carbonyl group.
Exactly, and this type of reaction where a nucleophile adds to a carbonyl group is fundamental to organic chemistry.
Okay, I'm starting to see how these concepts all connect. But what about other types of nucleophiles? Are there some that are even more powerful than cyanide?
There are. Get ready, because this is where it gets really interesting. We have a whole class of powerful nucleophiles called organometallic reagents. These compounds, like organolithiums and Grignard reagents, contain a highly polarized bond between carbon and a metal, like lithium or magnesium.
So what makes these organometallic reagents so special?
Well, because of that highly polarized bond, the carbon atom becomes extremely electron-rich, making it a supernucleophile.
A supernucleophile. Wow, so it's like a molecular superhero ready to react with anything that has even a slight positive charge.
Exactly. These reagents are essential tools in organic synthesis. They readily attack carbonyl compounds, forging new carbon bonds and leading to the formation of alcohols. They're like the master builders of the molecular world, creating complex structures from simpler building blocks.
I love that analogy. It really helps visualize how these reactions work. This has been an incredible journey so far.
It has. And we've only just begun to explore the vast landscape of organic chemistry.
I can't wait to see what other molecular marvels await us. I'm starting to see how understanding the fundamental properties of atoms and bonds is key to unlocking the secrets of organic chemistry. But the textbook also delves into a variety of reactions. Can we talk about those? For example, elimination reactions, they sound pretty intense.
They can be. Elimination reactions are all about removing atoms or groups from a molecule. Often, it results in forming a double bond. Think of it like creating space on a molecular dance floor.
Creating space for a dance floor, I like that analogy. But why would a molecule want to eliminate atoms in the first place?
Sometimes it's about achieving a more stable configuration, kind of like finding a comfortable position on that dance floor.
Yeah.
Other times it's a strategic step, like choreographing a complex dance routine in a multi-step synthesis.
Okay, so there's a purpose behind this molecular downsizing. Can you walk me through an example of an elimination reaction?
Sure, let's take the example of converting an alkyl halide to an alkane. Imagine an alkyl halide as a carbon chain with a halogen clinging on, like a wallflower at the edge of the dance floor.
I can picture that. So how do we get this wallflower to join the dance?
We can treat this alkyl halide with a strong base. The base acts like a friendly dance partner, grabbing a hydrogen atom from a carbon next to the halogen. As the hydrogen leaves, so does the halogen, and a double bond forms between those two carbons. Now they have room to dance.
So it's like the base and the halogen are escorting the hydrogen off the dance floor, creating space for the carbons to form a double bond and really show off their moves. But the textbook mentions different types of elimination reactions, like E1 and E2. What's the difference between them?
It comes down to the timing and coordination of those dance moves. In an E1 reaction, the elimination happens in two steps, kind of like a two-part dance routine. First, the halogen leaves, creating a carbocation, positively charged carbon atom. It's briefly on its own. And then in the second step, the base removes a hydrogen from a nearby carbon, and that leads to forming the double bond.
So it's like a solo, then a duet. What about the E2?
In an E2, everything happens at once, like a perfectly synchronized group dance. The base removes the hydrogen, the halogen leaves, and the double bond forms, all in one smooth, concerted step.
Okay, so it's all about the choreography of the reaction.
Yeah.
How do chemists decide which type of elimination to use?
Well, it depends on several factors. The structure of the molecule, the strength of the base, and even the solvent we're using. It's like choosing the right music and dance style for the occasion.
It sounds like chemists need to be quite skilled choreographers.
They do. And speaking of different dance styles, let's talk about addition reactions. They're, in a way, the opposite of elimination reactions.
So instead of clearing the dance floor, we're adding more dancers.
Exactly. Atoms or groups are added across a double or triple bond. It's like inviting new dancers to join in and create a more complex routine.
Okay, I'm intrigued. Can you give me an example of an addition reaction in action?
Certainly. Remember when we talked about bromination of alkenes earlier?
Yes, where bromine adds across the double bond.
That's a classic addition reaction. Imagine a bromine molecule approaching an alkene, which has that double bond, an open invitation to join the dance.
So the bromine molecule sees this open invitation and can't resist joining the party.
Exactly. The bromine molecule adds across that double bond, with each bromine atom attaching to one of the carbons that were previously double bonded. This creates a new molecule with two bromine atoms attached.
It's like the bromine molecule splits in two, and each bromine atom finds a new dance partner. But the textbook mentioned that this reaction is stereospecific. What does that mean?
It means that the way the bromine atoms add across the double bond isn't random. The stereochemistry of the starting alkene dictates the stereochemistry of the product. It's like having a designated spot on the dance floor for each bromine atom.
So it's not just about who's dancing, but where they're standing in relation to each other.
Precisely. This control over the three-dimensional arrangement of atoms is crucial, especially when synthesizing molecules with specific biological activity.
Makes sense. After all, in a complex dance routine, the position of each dancer is critical to the overall performance. But the textbook also delves into the world of enols and enolates. Can we talk about those? They sound a bit mysterious.
They are quite intriguing. Enols and enolates are key players in many organic reactions, but they're often hidden in the background, like stagehands, who ensure the smooth running of a performance.
Okay, I'm curious to learn more about these behind-the-scenes molecules. Can you explain what they are?
Think back to carbonyl compounds, those molecules with a carbon double bonded to an oxygen. Enols are isomers of carbonyl compounds, meaning they have the same atoms but they're arranged differently. In an enol, a hydrogen atom has shifted from a carbon next to the carbonyl group to the oxygen atom itself.
So it's like a molecular game of musical chairs with the hydrogen atoms switching places.
A great way to put this process of the hydrogen atom shifting back and forth is called tautomerization. Now, an enolate is the conjugate base of an enol, formed by removing a proton from the oxygen atom.
So an enolate is like an enol that's ready to react, a dancer who stepped onto the dance floor.
Exactly. And what makes enolates so important is that they are excellent nucleophiles.
Nucleophiles again. So they're attracted to electron-deficient centers, like that carbon in a carbonyl group.
Precisely. Enolates are key players in reactions like alkylations and aldol reactions, which are essential for forming carbon-carbon bonds and building more complex molecules.
So they're like molecular matchmakers, bringing carbon atoms together to form new bonds.
Exactly. And their matchmaking skills stem from the fact that the negative charge in an enolate ion is spread out over multiple atoms. This makes it more stable and more nucleophilic.
So it's like the negative charge is delocalized, making the enolate more comfortable being electron-rich and eager to share those electrons with a willing partner.
That's a great way to think about it. And this delocalization is what makes enolates such powerful nucleophiles, driving a wide range of reactions.
I'm starting to see how these seemingly small details about electron distribution can have a huge impact on a molecule's reactivity. Can you give me an example of an enolate in action?
Certainly. Let's consider alkylation reactions. We can use a strong base to generate an enolate ion from a carbonyl compound. This enolate can then react with an alkyl halide, like methyl iodide, in an SN2 reaction.
SN2, that rings a bell. It's a substitution reaction where one group is swapped out for another, right?
You've got it. In this case, the enolate, being a good nucleophile, attacks the carbon atom attached to the halogen in the alkyl halide. It's like the enolate cuts in and steals the carbon away from the halogen, forming a new carbon bond in the process.
So it's like a molecular dance battle, with the enolate ultimately winning over the carbon atom, but the textbook also mentioned the aldol reaction. Can you explain that one?
The aldol reactions are the classic example of enolate chemistry. It's a powerful tool for creating new carbon bonds between carbonyl compounds.
So it's like a double date for carbonyl compounds, facilitated by an enolate matchmaker.
Exactly. In the aldol reaction, one carbonyl compound provides the enolate, which then attacks the carbonyl carbon of another carbonyl compound.
So one carbonyl compound is essentially offering its enolate as a dance partner to another carbonyl compound. And this leads to the formation of a new carbon bond.
Precisely. This creates a new molecule called a beta-hydroxycarbonyl compound, also known as an aldol.
It's like the two carbonyl compounds have joined hands through a new carbon-carbon bond, forming a more complex molecular structure.
A perfect analogy. And this aldol product can then undergo further reactions, such as dehydration.
Dehydration, so it loses a water molecule. Is there a purpose to that?
Yes. Losing a water molecule creates a double bond between two carbon atoms, forming an alpha-beta unsaturated carbonyl compound. These compounds are themselves versatile intermediates in organic synthesis.
It's like the aldol shedding a layer, becoming even more elegant and reactive in the process.
Exactly. And here's something else that's fascinating. The aldol reaction can occur within the same molecule if the molecule has two carbonyl groups positioned just right. This leads to the formation of a ring.
Wow, so it's like the molecule is doing a self-aldol reaction, folding in on itself to form a ring. That's incredible.
It is. This type of reaction is incredibly useful for synthesizing cyclic compounds, which are found in many natural products.
Okay, so we have alkylations where enolates react with alkyl halide and aldol reactions where enolates react with carbonyl compounds. But the textbook also mentions the clayden condensation. How's that different?
The Clayden condensation is similar to the aldol reaction, but instead of aldehydes or ketones, it involves esters.
Esters, those are derivatives of carboxylic acids, right?
Right. Esters have a carbonyl group attached to an oxygen that's also bonded to another carbon group. Now, in the Clayden condensation, an ester enolate attacks another ester molecule, forming a beta-keto ester.
So instead of two aldehydes or ketones joining hands, we have two esters doing the molecular tango.
Exactly. And just like in the aldol reaction, this beta-keto ester product can be further modified. For example, through decarboxylation, where it loses a carbon dioxide molecule.
So it's like the beta keto ester is shedding a layer to become a ketone. It's fascinating how these reactions can be used to transform molecules step by step.
It is. And speaking of transformations, let's talk about another intriguing type of reaction, conjugate additions.
Conjugate additions, I remember that term. It has something to do with nucleophiles attacking a position next to a carbonyl group, right?
Exactly. Remember when we discussed alpha, beta unsaturated carbonyl compounds? These compounds have a double bond adjacent to the carbonyl group.
Right, so the carbonyl group is conjugated with the double bond.
Precisely. And in conjugate additions, also known as Michael additions, a nucleophile doesn't attack the carbonyl carbon directly. Instead, it goes for that beta carbon, which is the carbon next to the carbonyl group.
So it's like the nucleophile is drawn in by the double bond, but then makes a strategic move to attack the neighboring carbon.
Exactly. And this type of addition is incredibly valuable for adding groups to specific locations and molecules.
Can you give me an example of a conjugate addition in action?
Certainly. Let's consider the reaction of diethylmalonate with diethyl fumarate. Diethyl fumarate is a great Michael acceptor because it has two electron-withdrawing ester groups attached to its double bond.
Electron withdrawing, so those ester groups are pulling electron density away from the double bond.
Exactly. This makes the beta carbon even more electron deficient and a prime target for a nucleophile. Now, if we treat diethylmalonate with a base, it forms a malonate enolate.
So we're back to enolates. They really are versatile players in organic chemistry.
They are. Now, this malonate enolate, with its negative charge and eagerness to share electrons, attacks that beta carbon of diethyl fumarate, forming a new carbon-carbon bond.
It's like the malonate enolate is bridging the gap between two molecules, forging a new connection. I'm starting to see how these conjugate additions can be used to build more complex molecules.
They are powerful tools for molecular construction. And did you know that there's a reaction called the Robinson annulation that combines a conjugate addition with an intramolecular aldol reaction?
The Robinson annulation, I vaguely remember that from the textbook. It sounds pretty complex.
It is a multi-step reaction, but it's incredibly elegant. Imagine starting with a cyclic ketone and an alpha, beta unsaturated ketone. First, a conjugate addition takes place, where the enolate of the cyclic ketone attacks the beta carbon of the alpha, beta unsaturated ketone.
So it's like the cyclic ketone is reaching out and grabbing hold of the alpha beta unsaturated ketone, forming a new bond.
Exactly. This creates a product with two ketone groups. Then, in a remarkable feat of molecular origami, an intramolecular aldol condensation occurs between those two ketone groups, forming a new ring.
Wow, so the molecule is folding in on itself, using its own functional groups to create a ring. That's amazing. What happens next?
The final step is a dehydration, where the molecule loses a water molecule, forming a double bond within that newly formed ring.
So it's like the molecule is tightening its belt, creating a more rigid and stable ring structure. This Robinson annulation sounds like a powerful tool for building complex molecules.
It is. It's widely used, especially for creating intricate ring systems found in many natural products.
I'm starting to appreciate how organic chemistry can be used to create such a diverse range of molecules. But I have a question about something that keeps coming up. Stereochemistry. It seems like the three-dimensional arrangement of atoms is really important.
You're absolutely right. Stereochemistry plays a crucial role in determining a molecule's properties and reactivity. Luckily, chemists have developed clever ways to control stereochemistry in reactions.
Really? Can you give me an example?
Sure. Let's think about aldol reactions. We know that the enolate can attack the carbonyl compound from either side, potentially leading to different stereoisomers.
Stereoisomers. Those are molecules with the same atoms connected in the same order but arranged differently in space, right?
Exactly. And sometimes we want to make only one specific stereoisomer. One way to control this is by using a chiral auxiliary.
A chiral auxiliary. What's that?
It's a molecule that is itself chiral, meaning it exists as two non-superimposable mirror images, like your left and right hand. By attaching a chiral auxiliary to one of the reactants, we can influence the stereochemistry of the product.
So it's like the chiral auxiliary acts as a guide, steering the reaction to favor the formation of one stereoisomer over the other?
Exactly. It creates a steric environment that biases the reaction towards a particular outcome. It's like having a choreographer guiding the dancers to move in a specific way.
That's a great analogy. So chiral auxiliaries are like molecular chaperones, ensuring that the reaction goes according to plan.
Precisely. This type of stereochemical control is essential in fields like pharmaceuticals, where the wrong stereoisomer of a drug can be ineffective or even harmful.
Makes sense. If the molecule isn't shaped correctly, it might not fit into the biological target it's supposed to interact with.
Exactly. So chemists are constantly developing new and creative ways to control stereochemistry and create molecules with the desired three-dimensional structures.
This is all so incredibly fascinating. I'm starting to see the intricate beauty of organic chemistry, how every detail matters, from the arrangement of atoms to the choice of reaction conditions.
It's true. Organic chemistry is a fascinating dance of molecules, where structure, bonding, and reactivity are all intertwined.
I'm ready to learn more. But before we dive into the next topic, can we take a moment to recap what we've covered so far in this deep dive?
Of course. We started by exploring different types of reactions like eliminations, where atoms are removed to form double bonds, and additions where atoms are added across double bonds. We talked about how the stereochemistry of the starting materials can influence the stereochemistry of the products.
Right. And then we delved into the world of enols and enolates, those versatile nucleophiles that drive reactions like alkylations and aldol reactions, forming new carbon-carbon bonds and creating more complex molecules.
We also touched upon the clayden condensation, which is similar to the aldol reaction but involves esters, and the Robinson annulation, a multi-step reaction that elegantly constructs six-membered rings.
And we discussed the importance of controlling stereochemistry in reactions, highlighting the use of chiral auxiliaries to steer reactions towards specific stereoisomers.
It's been quite a journey so far, exploring the fundamental concepts and reactions that make organic chemistry so fascinating.
I'm eager to continue our exploration. I've been thinking about how organic chemists approach building these complex molecules. It must be like planning a major construction project, figuring out the best sequence of steps and materials.
That's a great comparison. That's where retrosynthetic analysis comes in. It's a really powerful tool that helps chemists plan organic syntheses. It works backward from the target molecule to simpler starting materials.
So instead of trying to build it from scratch, they start with like the finished blueprint and kind of deconstruct it.
Exactly, like taking apart a complex Lego structure to understand how it was built, what pieces were used.
Okay, I like that analogy. So how do chemists actually break down the molecule in retrosynthetic analysis?
They look for key functional groups and strategic bonds they can disconnect. They often use what are called synthons.
Synthons. Those sound a bit abstract. What are they exactly?
Think of them as idealized molecular fragments. They represent potential reactive units. They help chemists visualize how the molecule could be assembled from simpler pieces. It's like identifying those key subassemblies that need to be connected to create that final product.
So it's like reverse engineering the molecule to figure out the best way to put it together?
Precisely. And once they've identified those synthons, then they can start thinking about the real reagents and reactions they could use to make those bonds.
So it's like brainstorming the best crew and tools for the job.
You got it. Retrosynthetic analysis helps chemists develop these efficient and elegant routes to complex molecules. For example, let's imagine we want to synthesize a drug, like phenoglycol. It has an interesting 12-alkyl-2-diol motif, which means there are two hydroxyl groups on adjacent carbon atoms.
Okay, so we have our target molecule. How would we approach this using retrosynthetic analysis?
Well, one way to make 1-viryl-2-diols is to start with an epoxide. That's a three-membered ring with an oxygen atom. Epoxides are really reactive and readily open up when attacked by, well, you guessed it, nucleophiles.
Nucleophiles, again, they really do seem to be involved in a lot of organic reactions.
They are. So, in our retrosynthetic analysis of phenoglycol, we could disconnect that 1-viryl-2-diol motif to an epoxide synthon and a cyanide synthon.
So it's like breaking that 1-viryl-2-diol bond in our minds and imagining an epoxide and a cyanide ion as the two pieces.
Exactly. And that disconnection guides us to think about how we could actually make the epoxide and then open it up with cyanide to get our target molecule.
It's like working backward from the finished puzzle, figuring out the individual pieces and how they fit together. I'm starting to see the power of this approach. But what happens if there's a functional group in the molecule that might, interfere with a reaction?
That's a great question. That's where protecting groups come in. They're like molecular shields that temporarily mask that reactive group, preventing it from reacting too early.
So it's like putting a protective cover on a piece of furniture during a renovation.
Exactly. Let's say we want to make a Grignard reagent, which is a very powerful nucleophile. But our molecule also has a ketone group, which we know is very susceptible to attack by those nucleophiles.
So if we're not careful, the Grignard reagent might attack the ketone instead of doing what we want.
Exactly. So that's where a protecting group for the ketone comes in. We can convert the ketone into an acetyl, which is stable under those conditions we need for the Grignard reaction.
So it's like putting the ketone in a protective bubble while the Grignard reagent does its job.
Precisely. And once that Grignard reaction is done, we can easily remove that acetyl protecting group and reveal the ketone again.
It's like taking the cover off once the renovation is done. But are there protecting groups for other functional groups?
There are. Chemists have developed a whole toolbox of them. For alcohols, amines, carboxylic acids, the choice really depends on the specific reactions and conditions involved.
So it's all about choosing the right tool for the job, making sure the protecting group works with the other steps in the synthesis.
Exactly. It's a delicate balancing act, but it's essential for successfully making these complex molecules.
It's incredible how chemists have figured all these strategies out. It really is like a form of molecular artistry.
It is, and this deep dive has really only scratched the surface. The world of organic chemistry is vast and fascinating.
I feel like I've gained a whole new appreciation for this field. It's amazing how these seemingly small details, like the placement of an atom or the choice of a protecting group, can have such a big impact.
It's true, and that's what makes organic chemistry so challenging and so rewarding. It requires a deep understanding of the fundamentals, a creative mind, and a willingness to experiment.
Well, I have to say, this deep dive has definitely sparked my curiosity about organic chemistry. I'm ready to keep learning more and see where it takes me.
And remember, this is just the beginning. Organic chemistry is constantly evolving. There are new discoveries and applications all the time. So keep exploring, keep asking questions, and who knows what molecular marvels you might uncover.
Thanks for joining us for this deep dive into the world of organic chemistry. We hope you've enjoyed the journey as much as we have. Until next time, keep those knowledge-seeking gears turning.